Welcome, nerds. Today we're going to put a nail in the coffin of Chapter 4. It's done. We're finished with it. This is it. Last day. Oh, and I forgot to say before I started the recording, since we're going to finish these notes a day earlier than I planned, we're going to have our test a day earlier than I planned. It'll be Wednesday of next week, not Thursday. Okay? That means Thursday, the day before spring break, you will just make up work that you owe me, tests that you owe me, and retakes that you wanted to do. Okay? We'll have the class period for that. There it is. So, one-day lesson, we review Monday, Tuesday, test Wednesday, Thursday, we take an easy day before spring break. That wasn't the plan. It's just that this lesson is not going to take me as long as I thought. Because why? Because you're all smart nerds, that's why. All right, so binomial expansion is what we are talking about. In a previous lesson of this chapter, we had to do some polynomial arithmetic. We added, we subtracted, oh, that's right, and we multiplied. And the multiplication that I had you do really wasn't all that bad because it was literally just, multiplying two binomials. Or, worst case scenario, in the notes I gave you f times g times h. One of those three was a monomial. So all that did was change the coefficients and the exponents. It really wasn't bad. In the homework, though, I gave you a very special example. In the homework of that lesson, I gave you one that said find gg of x, which was literally function g times function g. And function g was a binomial. What is a binomial? It's made up of two parts. This is a binomial. This is a binomial. I was nice and I didn't ask you to find GGG of x or, GGG of x. I could have, but it would have required so many distributions. You probably wanted to pull your teeth out. I saved that for today. Don't worry, we will all walk out of here with all of our teeth. Okay? Let's go ahead and do a plus b quantity squared. That means a plus b times a plus b. And you know that you should FOIL here. The distribution process, right? So we've got a times a times b times a, and b times b. So we've got these four multiplications. The first one, a times a, will get us a squared. And then we've got a times b, which is positive ab. B times a, well, that's ba, but, we should try to keep our stuff alphabetic, so ab. I don't know, there's a joke in there somewhere about mathematics being ba or me being ba, but I don't know, I wasn't thinking on the fly. And lastly, b times b is b squared, and we have like terms. Right here in the middle, we can add those up. A squared plus 2ab plus b squared. That's not so bad. In fact, you learned this formula in Algebra 1, and we did it again this year in Algebra 2. This is a perfect square trinomial. We forced these to occur when we were trying to complete the square so we could solve quadratics by completing the square. You may or may not remember that, but we did do that this year. Forcing perfect square trinomials, which completes the square. Not too bad. So this was like finding GG of x, like I had you do in the homework. But what if I said a plus b to the third power? Well, you'd have to do, a plus b times a plus b times a plus b. Luckily, we already know what the first two a plus b's will give us when we multiply them. These two give us this statement right here. A squared plus 2ab plus b squared. But we still have this other a plus b out here. Oh my gosh, that's going to be 6 distributions. Yuck. I'm not going to draw the lines because they take up a lot of space when there's 6 of them and not 4. Okay? So instead, I'm just going to say them point and write. A squared times a gets me a to the third. a squared times b gets me a squared b. 2ab times a is 2a squared b. 2ab times b, 2b squared, 2a b squared, excuse me, I forgot to say a. B squared times a, but let's keep our stuff alphabetic. And b squared times b. Now we have to go through, track down our like terms, and combine them. Luckily, the order in which I did this multiplication, meaning I had the perfect square trinomial written first, forced all of my like terms to be right next to each other. Convenient. So when we combine our like terms, we will get a cubed plus one of these plus two of these, 3 a squared b's, plus 2 of these plus one of them, 3 ab squareds, plus b to the third. I mean, it really wasn't difficult, but it did kind of stretch out the time that that one thing took, right? And that was only to the third power. What if it was the fourth power, fifth power, 19th power? Wouldn't that just be awful? It'd be terrible, right? I mean, even the fourth power, I'm looking at it going, oh my God, I don't want to do that. Here's what you would have gotten if you had used to the fourth power. And what I'd like you to notice in these expansions is even when b was missing, like right here, it's written in just with the power of 0. And when a was missing, like right there, it's written in with the power of 0. And the same thing happened here with the purple one I just did. There were no b's in this term, so there's a b to the 0. And here at the end, there were no a's, so I put an a to the 0. And when the coefficient isn't there, it's just a 1, so the 1's are there. Look at what the fourth one is like. Oh my gosh. And I used to have a fifth one on there, but to save space, I deleted it because I didn't think it was necessary. I could fill it in right now if I wanted to. But that's because I recognize the patterns. Time for me to help you see the patterns. First, look at any one of these rows. Look at this last row. Look what's happening to the power of a. Look what's happening to the power of b. What do we see is happening to the power of a in every one of those rows? It's decreasing by 1 at each term, right? And what is the maximum power of a in each one of those expansions? The exponent of the binomial. So each one of these begins with a to the n and ends with a to the 0. Each one of these begins with b to the 0 and ends with b to the n. So at each term, I'm losing an a, but picking up a b. Losing an a, picking up a b. What do these two exponents add up to? What about these two? Melissa, what do you see? And there? So, and these both add up to 3, 3, 3, 3, 2, 2, 2. Every term of the expansion, the powers of a and b will always add up to n, whatever n was. So the patterns of the exponents are actually very easy to track. For a, start with power of n and decrease until you get to power of 0. For b, start with power of 0, increase until you get to the power of n. So every single one of them, the powers will add up to n. That's the easy part. What's not the easy part is the numbers that sit in front of our variables. What do we call those numbers that sit in front of variables? Coefficients. This is a binomial This is a binomial expansion. The numbers then that sit in front of every one of my terms are known as the binomial coefficients. And there is a pattern to those as well. That pattern is called Pascal's triangle. Every number you see in this triangle is known as a binomial coefficient. This is Pascal's triangle. And every number in this triangle has a very simple way of finding it. Allow me to write in row 6. Oh, by the way, I should have said that. We begin at row 0. Row 1, row 2, row 3, row 4, row 5. Allow me to write in row 6 and see if you can tell me how I found the numbers for that row. This is row 6, meaning a plus b to the 6th power. The coefficients in front of my variable expressions will be 1, 6, 15, 20, 15, 6, and 1. Do I have those memorized? No. Who can tell me how I found them? Who sees it? You added what now?
1 and 5, 5 and 10, 10 and 10.
Ah. What you're saying is, to find a number of a row, you add the two numbers above it. Yep. See, like this 2? That's the sum of 1 and 1. This 6, that's the sum of 3 and 3. So on and so forth. Pascal's triangle is insanely useful. It's all over the place in mathematics. And not because we made it be there, because we discover it all over the place. I discovered it once by accident in some calculus that I was doing. We know that human beings have had knowledge of this thing for like 5,000 to 8,000 years. Long before the mathematician Pascal put it in a book. We know that we had knowledge of it as humans because we've found it in like ancient Sumerian text and things like that, which is like the oldest written language on the planet. It's all over the place. It's crazy. And it's loaded with patterns. First one, I don't even know if you would call it a pattern. But without looking here, who could tell me how I know that this was row 4? That this was row 5, that this was row 6? Which number? The second number in every row is the row number. This is row 6, this is row 5, this is row 4. Every row begins and ends with a 1. But the second digit, and by that logic, the last digit, is always the row number. What's really cool about that is Pascal's triangle is symmetric. You could cut it in half. And its left and right sides are identical. Isn't that neat? In fact, because of that, some more upper-level mathematics that we call the binomial theorem, in other parts of the world, they teach it with A and B's exponents switched than what we do here in the States. And it's because it doesn't matter. Because Pascal's triangle is symmetric, which is really neat. Other neat patterns. I'd like for you to take a moment, look at maybe 1, 2, or 3 of the rows, and add up the numbers in that row. Just take a moment. Add them up. Pick a row. Add them up. Then pick another row. Add them up. Maybe pick a third row. Add them up. And tell me what you notice about the sums of the rows. Okay, Donald, what do you think you see? Row squared. So these numbers here add up to 25. Hold on. You're close. You're close. You're on to something. Alyssa?
1
Multiply what by 2?
The previous number. Previous sum.
Yes. Okay, that's not wrong. That establishes a recursive sequence. She said you could take the previous sum and multiply it by 2 and you'll get the next sum. But how would we say that so that it wasn't recursive, so that it was explicit? You're going to be able to talk around that, Hot Pockets you're eating, Daniel? Come on. What's the sum here? There it is. Each one of them has a sum of 2 to the power of n. This row adds up to 32. That's 2 to the 5th. This row adds up to 64. That's 2 to the 6th. Which is why, Alyssa, excuse me, that is why every sum is 2 times the previous sum. But that's because the previous sum was also 2 to the power of its exponent. Isn't that neat? I think it's neat. I think it's pretty cool. There's more patterns, like more than we could even talk about in a class. You could have a whole math course on Pascal's triangle, the amount of times it shows up. It's great for probabilities. Those of you that are going prob and stats next year, there's a very important branch of probability. It's called binomial probabilities. Binomial probabilities, you do them all the time. You just didn't know it. Binomial probabilities are systems that only have 2 outcomes. Yes or no, on or off, heads or tails. These are binomial systems. So I could say, like, I flip a coin 6 times. What's the probability of getting exactly 3 heads? Or what's the probability of exactly getting 2 heads? Things like that. Those kinds of questions use Pascal's triangle. Now, what if I was asking you about an expansion of a plus b to the 18th power? Do we really want to draw out Pascal's triangle all the way out to row 18? No. Oh my gosh. That would be monstrous. I wonder how many terms that would have. Well, first of all, do me a favor. Count up the number of terms in a row, in 2 rows, in 3 rows, and tell me what you notice about the number of terms in a row. Somebody new that hasn't talked to me yet. I'm trying to get you guys awake and involved. Come on. Somebody new sees it. Just count up the number of terms in a row. Okay, Gabriel? It's n plus 1. It is. Look, this is row 2. It has 3 terms. This is row 4. It has 5 terms. Each row has n plus 1 terms. That tells me that row 18 would have 19 terms. If I asked you to do a plus b to the 18th, that expansion would have 19 freaking things. Okay, I'd never do that. It's way too much. But could I ask you to tell me the 3rd number in row 18 without you drawing out all 18 rows? I sure can. And the question is, how? The answer is, there's a formula for calculating these binomial coefficients. The binomial coefficients that you see in these expansions are the values of this function, where r is less than or equal to n. Another way of writing this function is like this, with a stacked n and r in a set of parentheses. It's not a fraction, and we wouldn't say n over r. Both of these are read the same way. They are read n choose r, also known as the choose function. And the choose function essentially says, how many ways could you build groups from a certain number of objects? For example, my table of gentlemen to my right, back here, David's table. There's 4 guys at that table. How many different ways could I build a team of 2 from those 4 guys? So look back there and quickly count up how many different ways you could build a team of 2 from those 4 guys. Someone let me know when you think you know. How many different ways could I build a team of 2 from those 4 people? Okay, Nick? It's not 12. Team of 2. Oh, you know what the problem is? Order doesn't matter. A team of 2, David and Colin is the same as Colin and David. So it's not 12. What would it be then? It'd be 6. So you were right about 12 if order matters. But when I'm just talking about a partnership, order doesn't matter. There's 6 of them. That, what I just said, is called 4 choose 2. Go to row 4. This is 4 choose 0. This is 4 choose 1. This is 4 choose 2. That's 4 choose 3. That's 4 choose 4. So 4 choose 2 is 6. 5 choose 2 is 10. 5 choose 3 is 10. Isn't that neat? 6 choose 2 is 15. But how are those calculated? Those are calculated using this formula, where exclamation point is a factorial. In factorial doesn't mean n. It's not excited. In mathematics, what that means is take that number and multiply it to all of the integers lower than it, all the way down to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So what we have here is n factorial divided by r factorial times the difference between the 2 factorial. Basically, this digit and this digit will always add up to that digit. But this allows us a really neat result here. Check this out. Can we agree that 5 factorial is 5 times 4 times 3 times 2 times 1, which is the same as 5 times 4 times 3 times 2 times 1. But how could I write 4 times 3 times 2 times 1 quicker? Was that? No, not as a number. It's 4 factorial. So 5 factorial is 5 times 4 factorial, which is the same as 5 times 4 times 3 factorial, so on and so forth. Every factorial can be broken down like that. And that is how we will calculate these numbers by hand, using the fact that every factorial can be broken down into products, and part of that product can be a factorial that is just smaller. And you'll see in the following example. We're going to use the choose function to figure out what the 5th number of row 8 is. That would be 8 choose 5. Oh, I need to tell you something on this right here. By definition and definition only, 0 factorial equals 1. Because every row in Pascal's triangle begins with a 1. That's because each one of these is that row choose 0. This is 6 choose 0, 5 choose 0, 4 choose 0. Like, for example, that table of 4 guys back there. How many ways can I pick none of them? There, I just did it. I picked none of them. There's one way. No, there's one way. It's the same way as saying, how many different ways can I pick all of them at once? 1. Because picking all of them has the same number of ways as picking none of them. 1. Okay? So 0 factorial is 1. Anyway, let's do 8 choose 5. This is how many different ways can I pick 5 people from a group of 8 people. By the way, coaches of teams that have lots of people on their team, they do this all the time. Melissa, You play beach volleyball? Okay, how many people are on the sand at once? 4? Oh, okay, on a team though. I was gonna say, shouldn't I supposed? Yeah. No. Okay. How many people from your team are on the sand at once? 2. How many people are on your team? Total team, yes. 16. So your coach has 16 people, but only 2 are on a sand on it once. That is 16 choose 2 different partnerships that could be on the sand at once. And I bet your coach knows which of those partnerships are more successful than others. Yeah, that's a lot of mathematics that your coach doesn't know they're doing. What games have 5 people on the playing field? Basketball. How many people are normally on a basketball team, though?
We have like
17. So there are 17 choose 5 different combinations of players on the court at once for one team. That's a lot. And I bet your coach knows which ones are good together and which ones aren't. Okay, so let's figure out what 8 choose 5 is. It is 8 factorial over 5 factorial times the difference factorial, so 3 factorial. Remember, these 2 numbers down here will always add up to that number right there. So the 8 and the 5 go there, and then this is the leftover. Cool with that? See, these 2 numbers down here will always add up to that number. So whatever it's this number, choose this number, those 2 numbers go right there. And then this is the leftovers, basically. So the 8 goes here, the 5 goes here, the other 3 go there. Because 3 and 5 make 8. Yeah, like if I asked you to do 16 choose 3, it'd be 16 factorial over 3 factorial, and then 13 factorial. Because these 2 numbers have to add up to the 16. Okay? Anyway, I'm not going to write 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, because that's 8 numbers. That's a lot of stuff. Instead, what I'm going to do is I'm going to think ahead and I go, I wish I could cancel some stuff off of the top and bottom. Oh, but I can. Because 5 is 5 times 4, 5 factorial is 5 times 4 times 3 times 2 times 1. And I'm pretty sure I said 5 times 4 times 3 times 2 times 1 when I listed out this thing's numbers. You see, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So those 5 factorials are going to cancel each other out. And then 3 factorial is just 3 times 2 times 1. So the 5 factorials, they go bye-bye. And what's 3 times 2 times 1? That's 6. So the 6's are gone too. Looks to me like it's just 56. 8 times 7. Yes? No. It's 5 times 4 factorial, which is just 5 times 4 times 3 times 2 times 1. Because I wanted to be able to do this by hand. I don't know what 8 times 7 times 6 is. But I do know that 3 times 2 times 1 is 6. So this 6 and this 6 cancel because this is all multiplication. Now here is how you'll use your technology to confirm when you're doing your homework. Because this is what I'm going to be looking for on your homework. I'll be looking for this. But you'll make sure you did it right with technology. Yes, the scientific calculator can do the choose function. The choose function resides in PRB. PRB stands for probability. Remember what I told you? We use it for binomial probabilities? That's why it's there. Probabilities. So you're going to do this. Eight, PRB, scroll over to NCR and hit enter. then 5, and hit enter. And you'll see there's 56 ways of building a team of 5 from 8 options. I mean, it's already on the paper. We might as well do it. Look at this. Look. 16 times 15 times 14 times 13 factorial, because I wanted the 13 factorials to disappear. Oh, and this is just 3 times 2 times 1. Well, the 13 factorials cancel. And it's not going to be, this one won't have a 6 in it, so I will have to reduce things separately. But what's 14 divided by 2? 7. And what's 15 divided by 3? 5. So the answer is 16 times 5 times 7. Whatever 16 times 35 is. It's 560. I just did 16 times 35. Because 14 over 2 is 7 and 15 over 3 is 5. Look at all those reducings that we did. Or I could just do 16 PRB NCR 3 equals 560. But I want to see that you know how to work with the choose function. I'm going to be honest with you. I plan on making your extra credit a did you fully understand this concept, and it'll be from the choose function's calculations and capabilities. That's what your extra credit's going to be about. I just told you. And because of that, you know you won't just be able to use your calculator to get it right. Oh yeah, I'm not going anywhere with it. But I do want to show you how to do it on this calculator. This calculator is going to operate differently. Its NCR command is right here above the 8. So 8 choose 5. 8, second 8, 5 equals. There it is. So now it's on the video. And we will say thank you to Donald for letting me borrow his calculator for the video. Melissa, come on, look. 8, PRB, NCR, enter, 5, enter. It's in PRB. Okay? Okay, so what were you freaking out about?
She's mixing up one to use the PRV. She used it on 16 and 35.
No, PRB, that means choose function. Here, there is no choosing. It's just 16 times 5 times 7. I used the choose function to write this out. But this is just multiplication. The choose function is that. Okay? All right. So we're done with the calculators. Let's go ahead and use Pascal's triangle to write out the expansion of this. That means write out the first 6 rows of Pascal's triangle, including row 0. Boom. There it is. That's not 1, 5, 6. That's 15 and 6. So this row has 7 terms in it. So we know this expansion will have 7 terms in it. The numbers in this row are the coefficients. Remember, at each step, we're going to lose an a, which is x, and we're going to gain a b, which is y. On the first one, so I'm going to raise this to the 6th power without any distributions. There are 1 of my x's to the 6th, y to the 0. But I'm not going to write y to the 0 because I don't need to. But are you all cool with the fact that there is a x6, y0 there? Yes? Okay. Plus 6 x5, y1. See? I lost an x, but I gained a y. Plus Next binomial coefficient, 15. Lose another x, x4, but gain a y, y squared. Next binomial coefficient is 20. x3, y3. Lose an x, gain a y. Plus 15. X squared, y4. Lose an x, gain a y. Plus 6. Down to my last x, but I do have 5 y's. And lastly, 1. Y to the 6th. Get skinny, math. We found the edge of the page. And it dodged the hole in the paper too right there. Man, I'm shaking like a leaf. I'm starving right now. Do you have questions for me about how to expand your binomials without doing distributions? You draw out Pascal's triangle on your homework. I left you space on the right side to take it out to whatever row it says. I think the biggest row is 6, because after that, we're starting to get into the territory of, man, that's a long polynomial, and I have no reason to do that to you. And then you're just going to put the coefficients on there, and at each step of the way, you'll lose an A, but pick up a B. Yes, Kelsey? Y plus X? Oh, you mean if you switch the order of this? Okay, when it's addition, no, order doesn't matter. But order subtraction does matter, which you'll see here. Because when I go to do this one, like for example, for this one, what we had was that A was X and B was Y. But when we go to do the next example, I have coefficients that are no longer 1s in front of my terms. And yes, if it's subtraction, order big time matters. But Pascal's triangle is symmetric, so you'll get the same, as long as you don't goof up the symbols, you'll get the exact same polynomial. It'll just be written in a backwards order. But like I said, other countries around the world, they'll do it backwards sometimes, and it doesn't matter because Pascal's triangle is symmetric. Yes, Max? The exponents. So x, A, begins with whatever this exponent is and ends with a 0. The B will begin with a 0 and end with whatever this exponent is. See? And at each term after that, I've lost an A but picked up a B. Okay? This way, the exponents of my variables always adds up to, well, the exponents of my A and B always adds up to n. Well, here n was 6. Okay, for this one, it's row 4, which is right here. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. A is 2x. B is negative y squared. When your B is negative, it's going to make your expansion oscillate between positive and negative, back and forth. Positive, negative, positive, negative, positive, negative. Kind of like geometric sequences does when you have a negative ratio, right? Alrighty. Binomial coefficient. N is 4, by the way. So binomial coefficient A to the n, which is 4. I'll even draw out B to the 0. And now every term after this, I'm going to lose an A, but I'm going to pick up a B. Plus, next binomial coefficient is 4. I lose an A, I gain a B. I'm going to have to write much smaller. I'm going to run out of space. lose an a, gain a b. Next binomial coefficient is 4. Lose an a, gain a b. And I'm not going to be able to squeeze it in there, so I am going to do the same thing I did in first period. Wrap down to the next row. Binomial coefficient is 1. I'm all out of A's now, but I have all 4 B's. And at this point, we just simplify. Ready to simplify? Awesome. Here we go. Anything to the 0 power is 1, so that doesn't matter, and that doesn't matter, so I won't even look at those. Here, 2 to the 4th, that's 16. X to the 4th. Times 1, still 16x to the 4th. Here, I have a single negative number, so product will be negative. 2 to the 3rd is 8. 8 times 4 is 32. X to the 3rd, y squared. Because power to power, you multiply. So 2 times 1 is 2. Now I have an even number of negatives, so this one will be positive. The product will be positive. 2 to the 2 is 4, and 4 times 6 is 24. X squared, power to a power, multiply, y to the 4th. Odd number of negatives, product will be negative. 2 to the 1st is 2, and 2 times 4 is 8. X to the 1st is just x, power to a power. 2 times 3 is 6. Y to the 6th. And lastly, an even number of negatives will be positive. 1 times whatever. Power to power, you multiply the exponents. Y to the 8th. And that is what you get if you raise this binomial to the 4th power. We did it, nerds!